In this video tutorial for Shape version 5, we are going to show how to import and visualize external volume data, such as those generated in 3D hydrodynamic simulations. To do this, we are going to create a proxy object in our 3D view. Let's say a sphere, doesn't matter really which kind of object. This will hold It's just a placeholder for our external data. Now in the general tab we can just change the name, say to external data. But then the important part is the render input, which we are going to change from mesh to ASCII. This is for ASCII input. So you should prepare your external data in ASCII format. Click on the input options on the right to the ASCII to the drop-down list. Then you get an input properties dialog where we are going to first select our file, clicking on the file name button. Okay. And next we have to take care of the how many data points are going to be read in one buffer, and it's useful to make these multiples of some slice of your simulation or input data, let's say 256 in this case. If you have sparse or very small input data file, then set it to 1, but otherwise it's convenient and faster to set this to some reasonable number in the hundreds. And then much care has to be taken at setting up how the data is read in this format string that we are going to change next. Our data have 10 columns. First, the positions in X, Y, and Z. We are using Cartesian coordinates, and then the velocity components in X, Y, and Z. And the default is set to read the density, or our quantity that is to be visualized, as n, and right after the velocities, but in our case this is actually the 10th column and is the emissivity. So we are going to change the position of the n to the end. Delete that and replace it by some dummy variable that we're not using actually in shape, like d, such as d, and place the n to the end separated by a comma. Make sure that no spaces are in this format string, and they're all separated by commas, although the actual columns in our input file may be separated by a different separator character, which is set further down here. In this column separator, we can select between space, tab, or some other character that you can set manually. Now then we have we might not want to read every line in every data point in our data set. Then set the n to a number larger than 1, and the lines per entry in our case is 2. To every volume point we have 2 lines. They are separated into 2 lines, and important it is to set, if it applies, the CGS flag, which automatically converts CGS units of distance and velocity to meters in terms of distance, and kilometers per second for velocities. Densities are converted to kilograms per cubic meter. And then we are setting the center. Our data are not centered on the origin, on the coordinate origin. Therefore, we are going to set the position of our center here the x coordinate, y and z coordinates. This will recenter our simulation space on the coordinate center in shape, which makes it easier to rotate and manipulate the data in the visualization. Alright, here this should be basically it. Our CGS conversion is set, and we have to use meters in the center. Our preview of the data shows that there are 5 columns and 2 lines per data point. Make sure everything is alright. Our quantity of interest is set in the correct column. Separators are right. Our center is correct. No, the last coordinate in our case is not correct because we're not having a cubic volume. It's twice as long in Z. Okay, done. The next issue is that we're going to delete the default density and temperature modifiers, so they do not interfere with what we are reading. And then we have to set a species. We have to generate a species that allows us to use our input as a spectral line emissivity, and we go to our physics module, select a new species, a new custom species, call it line, and then enable emission. It's already enabled, nothing else is enabled, which is fine. And then edit our emission coefficient. We're going to set up a Gaussian spectral line proportional to our emissivity, which is in the n variable. We select a Gaussian template, apply that, go back to our function, edit the default Gaussian function, delete the coefficient and replace it by n, and then set our the position and width of our spectral line to 5000 angstrom in position and a suitable width of a few kilometers per second. Let's say 2 times 10 to the minus 11 meters. Alright, that should be that. We now go back to the 3D object and apply the species. So click on the species tab. After selecting our object, open the drop-down list of all species that are available, select the line and click add to add this to our object. Right, then we go to the render module and set up our renderer, which has to be the physical renderer to get sensible results. We could now select real-time rendering, which is the one that makes things fast after loading all the data. Right, everything else should be the same. The grid size is okay, 128. Could be bigger, but to speed things up now for our test, we leave it at that, and we set our central wavelength to 5000 angstrom, which is the position of the line, and our bands, the number of bands is 150 roughly. That's what we should to have good resolution. And then the upper end of our spectral range should be 5.05 times 10 to the minus 7, and a similar amount below the central wavelength. That gives us a range of about 2000 kilometers per second, which we are going to set in the group tab, selecting our primary display to enable that, and set our range to 4000 which goes then from minus 2000 to plus 2000 around our central wavelength. And the importing grid has already started since we enabled the real-time rendering, which starts whenever we change one of these parameters. And it has started reading the grid. You can see the percentage, and we're going to, in the meantime, set our no, we have to stop this because an important parameter before reading the data has to be the image size, or our cube size. In the image tab, we set this to a width of 7.5 times 10 to the 15, which is our biggest extension of our cube. And it has to be 15 because we're now counting in meters, not in centimeters. So it's 100 times smaller than what we used for setting the center in the other dialog. And the height of the slit we're going to set to 15 times 10 to the 15, which covers the whole object, and the width to some fraction of that. Every time we do that, it tries to render real-time, do a real-time rendering, but doesn't have any sensible data. So nothing shows, and that should be about it. Let's look at it at an angle of 90 degrees. So we can see the bipolar object that we are going to visualize, and click on render. Then it starts importing, and this will take a few minutes. Let's wait until the percentage shows so everything goes all right. At the bottom you can see the progress bar is now turning into a percentage, and it will take a few minutes to do this, and so we're going to pause the recording in the meantime, and I'll be back in a few minutes. Okay, we're back. It's almost done, and if everything went right, we have a visualization, right? There's something, and it's a very high contrast image, so we are going to change a little bit the color representation, or the color map or grayscale map first, and set this to a power, very small power, so we can see all the details. There you go. And a similar thing we do with the PV diagram. Okay, now we can see it. Maybe too much. Yeah, that's a bit better. Alright, and we can look at the color, the physical color of the 5000 angstrom line. And the spectrum, clicking on the spectrum image button above the visualizations. Here we go. And if you now want to change a new camera position or viewing angle, then you can change the inclination, for example, and a real-time ray tracing is done immediately without rereading all the external data. Takes just a few seconds. Now, while your visualization is being read from the disk, you could set up an animation, such as changing the inclination angle or some rotation of the object in space, selecting these two variables, inclination and world set, and set an analytic function to be just x, which is time in this case. Set the number of frames to 360 and time to 360. Important is to disable render and distribute. By default this is enabled, and otherwise it will, for every image, for every frame, it will read the data from disk, which would take forever. So disable that to get the real-time rendering to be effective. Enable 2D images and PV diagrams as output and disable all the others, and then click animate, and ray tracing will start immediately and start generating your images after it is done. It will now make a sequence of 360 images rotating the object around in inclination and around this axis. That's it for this video tutorial. Let us know if you have any problems. Thank you.